of the shape of a system. This is saying we've already got a capacitor with a measured value, but we are taking a single capacitor and adding it perhaps in series, or maybe even in series with a system that is in parallel. And this would be considered a system of capacitors, because it is we're taking a single capacitance and creating a group. And you might ask, well, why would you do this? Just get a capacitor of the size you want. Well, they don't make them in every size. So if you need a capacitance of 5 farads and they only have capacitors that are 2 farads, well, you might need to find a way to arrange them to get 5 farads of capacitance. You follow what I'm saying? So you resolve to making a system, and there are rules for how the system deals with capacitance. We're going to use Kirchhoff's laws to do that, but at the end of the day, it just comes out to be a formula. So I want to show you where these formulas come from, because it also is indicative of how Kirchhoff's laws kind of work. But when we're done, we probably won't use Kirchhoff's laws very much for this kind of stuff. We will probably use the rules that we kind of create here. And I believe we were starting with a system of capacitors that are in series. Again, this is a series element. I'm going to use the word element because as I just drew, you saw that that particular system had series elements and parallel elements, correct? So this is just a set of 2 capacitors in series. I could have put 8 capacitors in series. You also recognize that too, right? So what we get for 2 capacitors in series will extend to whatever number are in series. So C1, C2, a potential difference applied to the system. As we were talking on, whatever day we started this, if the battery has positive and negative here, a single charge particle, say a proton, pulled from this plate, right, would be pulled towards that side of the battery. That would create a single negative charge here. And as this is a battery that would pump that charge this way, that would create a positive charge on the other plate. Well, the positive charge in the top plate would push a positive charge out of the bottom plate, making the bottom plate negative and this plate positive. Can you kind of walk through that mental kind of dialogue with me? Due to Kirchhoff's second law, there's no junctions here. So the amount of charge that must be moved off of one capacitor has to be the same as the next capacitor in series. So the charge that is developed on capacitor 1 and the charge that's developed on capacitor 2 have to be equal for capacitors that are in series. That's a rule. I would write that down. Capacitors in series all have the same amount of charge. It's due to Kirchhoff's second law, conservation of charge. All good? Now, at the same time, we have Kirchhoff's first law, which says that the sum of the voltage drops in any loop of a circuit has to be equal to 0. And we addressed this a little bit by saying that you can choose your loop, and when doing so, we have to be careful, because although the phrasing is voltage drops, we have to kind of present this from a standpoint of whether when we go to a circuit element, is there an increase in potential in the direction of our loop or a decrease in potential in the direction of our loop? So when we go in the direction of the loop I've just drawn, starting with the battery, we're going from the negative to the positive side of the battery. That is an increase in potential. So we would make the battery positive. And a note about my little symbol there, that symbol E is called EMF. It isn't really the symbol for a battery. A battery is actually a pure potential difference. But the exam generally favors using the symbol for an EMF as a generalized potential difference. So I'm going to use that and introduce it now, since I know it'll probably be on the actual test for capacitance. Right? I pull any circuit diagram from the old AP exams, and they all have EMF instead of a battery symbol. All right. Now, if you'll notice, the next capacitor, C1, if I go in the direction of my loop, I go from the positive plate to the negative plate. You guys see that? That means that's a loss of potential, so I'm going to say negative V1 for the voltage across capacitor 1, and then the same for V2 for the voltage across capacitor 2, and I'll set that equal to 0. There are circuit elements where no matter what direction you draw your loop, they will always be negative. So things that consume energy are like that. Capacitors don't consume energy, they store energy. So their potential has to be judged by the direction of your loop. All righty? All right. Now you might be wondering why we're doing this. Let me tell you why we're doing this. What I'd like to be able to do is figure out what I actually, let me say that different. We're trying to figure out what the battery actually sees. The battery doesn't know that there's two capacitors there. The battery simply provides charge based on the total capacitance of the system. I generally say total capacitance, but the actual word I'm supposed to use is equivalent capacitance. But that's a lot to say, so I generally just say the total. But equivalent means if I could take these two capacitors out and replace them with a new capacitor, what would that capacitance be? Does that make sense to all of you? That's what we're trying to figure out. The battery merely supplies charge. So the battery doesn't know what's out there. So the battery's connected, it sees a circuit, it's going to supply charge to that circuit. In fact, from the standpoint of the battery, the total capacitance is going to be whatever total charge it pumps out there divided by whatever the EMF was. From the battery standpoint, that's what happened. Now, in talking about Kirchhoff's laws, the thing I want to remind you is that these circuits run on potential difference. And capacitance is defined as charge divided by potential difference. So we could rewrite this to say that potential difference equals charge times capacitance. Remember, I'm trying to figure out how the capacitances are related to the total capacitance. So I would like to take my Kirchhoff's law here and rewrite it in terms of capacitance, not in terms of the potential difference. Yeah?
Wouldn't it be charge divided by capacitance?
Yes. Thank you, Anthony. Mr. Shelton, not doing basic math. You saw it here first, folks. So let me rewind and say what I need to say again. We would like to take this statement and rewrite it in terms of the capacitance. We want this, because, this replacement doesn't depend on what battery I connect to it, right? It doesn't matter what battery I use here. I'd like to have something that's purely based on the capacitance. So we're going to try and rewrite this in terms of capacitance. First, I'm going to say I can make some replacements in here. I could write this as minus Q1 over C1 and minus Q2 over C2. That all has to equal 0. I also realize that from the standpoint of the battery, I could write the EMF as Q total over C total. So I get something that looks like this. Now, if I do just a very little bit of algebra, I can solve that and have it look like this. The total is going to be Q1 over C1 plus Q2 over C2. However, and I hope that you are a little forward-seeking, Q1 and Q2 are equal. And that must equal the total charge the battery pushed out. So that must mean that QT equals Q1, which equals Q2. Right? They have to all be the same amount of charge. So ultimately, they're all the same, which we can just put as Q. And if they're all the same, then we can factor out the Q and divide it away because we know it's not zero, and get that the total capacitance of a circuit is equal to the sum of the inverses. Well, that's no good. Now, this all looks kind of messy here, so let me clear this up just a little bit. If I want to take a circuit that has a system of capacitors that are in series, C1 and C2, and change it into a circuit that has just one capacitor, C equivalent, then to calculate the equivalent resistance, I add up the inverses. Now this, I don't know if you know the way the math is going to work on this, but this ultimately means that the total capacitance, when you put them in series, makes the total capacitance less. Let's demonstrate. Imagine you have a 3 farad capacitor and a 6 farad capacitor, and you put them together in series. Then the equivalent capacitance will be 1/3 plus 1/6, and then you have to invert that solution. So common denominator dictates here that this will be 2/6 plus 1/6, or 3/6. That's not the answer. To get the answer, you have to invert it. So the equivalent capacitance is 2 farads. Everybody see that okay? Any question about that? Now, it shouldn't be a surprise that the capacitance goes down when you put them in series. Think about it. If you put them in series, what you've really done is increase the separation distance between the plates, right? You're inserting more distance between plates. When you insert more distance between the plates, the capacitance goes down. So putting them in series reduces the overall capacitance. Of course, you might wonder, well, why would you bother to do that? Don't you want more capacitance? Not necessarily. What if your circuit required 2 farads of capacitance and all you had was 3s and 6s? This is how you would do it. There's more than just this. I want to demonstrate what you're supposed to be able to do with this. So now that you have this information, I want to talk to you about how we solve circuits using something called stepwise reduction. Stepwise reduction is a process for skipping Kirchhoff's laws and solving a circuit without using them. So let's go back to our circuit. Let's assume that we use our 6-volt batteries and we have our 3 farad and 6 farad capacitance. In order to do stepwise reduction, to solve our circuit, our goal is to be able to say, well, what is the voltage across this capacitor? What is the voltage across this capacitor? What is the charge across this capacitor? What is the charge across this capacitor? And how much energy do our capacitors store? That's what stepwise reduction's goal is going to be, to determine how our circuit behaves. So solving a circuit means being able to tell me any of those values for any circuit element in a complex circuit. The first part of stepwise reduction is reducing your circuit to a single capacitance? Well, you've just learned how to do that for a system that is in series. So, the first step of stepwise reduction is reducing your circuit to a single capacitance. This will often require multiple steps if you have a complex circuit. The next part is to solve for voltage and charge for your simplified circuit. Your next step is to solve for voltage and charge of your simplified circuit. So in this circuit, we know that the voltage is 6 volts because it's connected to just a single voltage source. And to figure out charge, well, I just use my expression for capacitance. Rearrange it to find charge, and then calculate the amount of charge that must be stored in the equivalent capacitance. 2 times 6 is 12. So I know the charge is going to be 12 coulombs. Now your next step, third step, is to step backwards, taking with you something you know about your prior circuit. In a series circuit, when we step backwards, we know that the elements of a series circuit all have the same charge. So we take the charge and apply it to every element that is in series. So I look at these two capacitors and I say this one must have 12 coulombs of charge and this one must have 12 coulombs of charge. Capacitors in series all have the same charge. That rule's important. Now that I've stepped backwards, I go to my circuit where I've just stepped backwards, and I compute whatever value is missing. In this case, the voltage is missing. So I want to compute the voltage, again using the same formula, Q equals CV, but now solving that for V. So V equals Q over C. So 12 divided by 3 gives me 4 volts. 12 divided by 6 gives me 2 volts. When you do stepwise reduction, every step has an opportunity for you to check your work. In the case of this particular step, capacitors in series, the voltage has to add up to equal the voltage that was there before. There was 6 volts across the equivalent capacitor. 4 plus 2 has to equal 6 volts. So you can check your work. Now, this one, you understand how ridiculously silly this example is, right? There's a single set of series. But I want you to imagine what you're going to be doing for real, which will be combinations of series and parallel. And you will have to be making small reductions to reduce your circuit, and then you'll be stepping back over multiple steps. The problem is we don't have the rules for a set of capacitors in parallel. We got to do that now. Parallel circuits are going to be a little bit easier though, or at least this derivation will be easier. Because when I'm dealing with a parallel circuit and trying to consider what the battery sees for a parallel circuit, the battery just sees a single capacitor, the equivalent capacitance. But if we have multiple ones in parallel, well, those capacitors each have individual capacitance. No. You probably realize that putting capacitors in parallel is probably going to make the total capacitance greater, don't you? You see how it looks like it's actually making the area bigger because you have multiple areas to spread your charge out? But we'll finish this up tomorrow, and we're going to do some complex circuits as our examples tomorrow.